Hello everyone, it's Wilson here. Let's continue to talk about setting up triple integrals. This time our solid is bounded by the paraboloid y equals 4x squared plus 4c squared and then the plane y equals 4. Okay, so the first thing is that we are going to draw the solid and see what it looks like. Okay, so the paraboloid, and then we also have the paraboloid bounded by the plane. So this is the solid that we have here. And then now the next thing is that we need to decide which coordinate plane that we should project the solid on so that we can set up the triple integral. It's actually a good idea to project on the xz plane this time, okay, compared to last week's video. The reason is really because we have a disk if we project on the xz plane. And how do we get this disk? This disk is actually found by finding the intersection between the two surfaces here. So the way that we do it is that we can plug the 4 into this y here, and then now we get this equation. So 4x squared plus 4c squared is equal to 4, and then simplifying it, then we are going to get x squared plus z squared equals 1. And so we are getting a unit disk here. Okay, so now we are basically ready to start setting up the triple integral. So we first write it as an iterated integral. And then now what really happened is that we are going to put the y as the innermost integral here. The reason for why we do that is because our projection is on the xz plane, as you can see. Okay, so we put the z and the x on the outside. Okay, so now the next thing, okay, is to think about what to put for the limits for the innermost integral. And to do that, we need to look at the solid, and sometimes it's not so obvious by just looking at the solid, so it will be a good idea to look at a sideways view for this one. And then you may say, how does that work? We can pretend that we are standing on the positive x-axis and look into the direction of the yz plane. And when we do that, then we will see something like this. Okay, so you can see that the positive x-axis is sticking out toward us in this of the screen. Okay, so now what really happens is that we see something like this, and we can actually just look at the lower bound. The lower bound in the y direction, because we're finding limits for the y. The lower bound in the y direction is actually this curve over here. And actually it's not the curve, it's actually the surface, but because we are looking at as a 2D graph, then we will just get a curve. And then we are going to just draw put a point randomly somewhere on this curve, and then just draw the arrow and then go to our upper bound. So this arrow here clearly shows that the lower bound is our paraboloid, and then the upper bound is what is the plane. And so now that becomes really easy because the lower bound is it's the paraboloid, so we just put 4x squared 4z squared as the lower bound. And then what about the upper bound? The upper bound is just the plane. And see that no matter which point that where you draw the arrow, it's always going to hit y equals 4, so we get a constant for the y, upper limit. Okay, so now once we figure out the innermost integral, then we just need to deal with the outer two, and that only requires us to look at the projection. And we don't need to look at the solid anymore. Okay, so now looking at the projection, because we need to find the limits for the z first. So we are going to break this circle into two pieces in the z direction. And when that happens, then we have the top semicircle and then the bottom semicircle. And then you can see that if we solve for z here, and then eventually we're going to get plus or minus of the radical. So that's why we have the top half and the bottom half, one with a plus and the other one with a minus. Okay, so what do we put for the limits? Because we already solved for z, so now we have those two as the limits for the z. And the outermost one is always the easiest one. The reason is really because we are going to get constants for the outermost integral, and that's for the x. And because this is a unit disk, so the limits will be easy to figure out. So we get a 1 to 1. So now we have set up the triple integral in rectangular coordinates. The problem is that when we try to evaluate this triple integral, we actually will have to deal with the square root, and that's hard to deal with. And so in that case, then it would be a good idea to use cylindrical coordinates. And then you may say, why? Because our projection is a circular disk, so it would be a good idea to use polar. So let's use cylindrical coordinates. And what are the conversion? Here are the conversion. The problem is that this time the projection is on the xy plane, not on the xy plane. So our usual conversion, which is x equals r cosine and y equals r sine, is we cannot use that anymore. We actually need to put the r sine for the z, and so y it's equal to itself. And because of that, okay, x squared and the z squared, when we add them together, we are going to get r squared. Okay, so now let's write down the integral, and you can see that because we are using the cylindrical coordinate system, the y is still equal to the y, so y would still just be itself, and then the dy will stay there. Now what about the dz dx? The dz dx is the dA. In this case, the dA will turn into r, and then dr d theta. Okay, so now we're ready. For the y limits, because we already have the y limits over here, we can just copy, but we cannot just use this one the way it is, because we have what? We have x and z here, but there was no x and z here. So we're gonna make the conversion, but it just happens that x squared plus z squared is r squared. If we have 4x squared plus 4z squared, then we should be getting 4r squared, so we get 4r squared. And then now, what about the upper limit? Look, upper limit is actually simple because that's a constant, so we are going to just get 4, okay? And then now, the next thing is the r. The r limits would be easy because we have a unit this here, so it's going to go from 0 to 1 for the r limits. And then for theta, theta is also going to be easy because we have a full circle of this. We go from 0 to 2 pi for the theta. And so now we are actually ready to do the calculation, okay? Now, generally the calculation will be tedious, so I'm not going to spend all the time to do that. What I'm going to do here is simply just to do what? It's simply just to outline the major steps, and then you can actually try it on your own, okay? So first thing, we are going to integrate with respect to y, and then we are going to get 1/2 y squared, and then we evaluate from 4r squared to 4. And then we plug those in, and then simplify. After that, then we need to integrate with respect to r, but there was an extra r on the outside, so we need to distribute the r first before we do the integration. So we'll just do that. And after we do that, then it becomes a polynomial in r, and this is easy to integrate. We just use the power rule, and then we need to plug in the 0 and 1. And so we plug the 0 and the 1 in there. I didn't show the 0 because when you plug in the 0, you get 0 here. And after doing the calculation, we just get a constant. And then integrate with respect to theta, then we get theta evaluated from 0 to 2 pi, so we are going to get 16 pi over 3 as the final answer. Okay, so that's it for this problem. There was one more thing that I want to mention before we end the video, is that you can see that at the beginning when we do the integration, there was no theta involved anywhere, except for the outermost integral. Okay, so when we run into this kind of situation, we could have done it with just getting 2 pi, because there was no theta, right? So the whole thing is constant in theta, so we can actually just integrate at the same time. So we just get theta, and then evaluate it from 0 to 2 pi, and then we just get 2 pi times the inner two integrals, and then we are still going to get the same answer, but that will just make the calculation faster. Okay, so that's the extra thing that I just want to mention here. So that's it for this video. Thank you for watching. I will see you next time.